This is section 6.2, day 3, and we're going to get back into, for the last part of this section, working with differential equations and that strategy for solving those equations. And in section 6.1, we call those initial condition problems. So we've done this in section 6 done. We're going to come back to it now, and we're going to come back to it in the next section as well. So we have a differential equation, and we use the term separable in front of it when we have a expression for a differential equation that looks like this. Now this looks a little kind of weird, but let me just explain it here. We have our Leibniz notation, dy dx. So we know it's a differential equation because we see a derivative. And so we say the derivative is equal to some expression with x's that are functions of x times some expressions that are functions of y. So we might have something like x squared times 2y. Or maybe we have something like e to the x times y to the third. Okay, so when we have a situation like that, and I'll get into this in a second, we can separate the x's and the y's. So we call those separable differential equations. And so what happens, like we'll look at this first example here in our notes, we have a differential equation. We know that because this is a dy dx here. It's written in prime notation instead of Leibniz. So we have a differential equation that says dy dx equals 2x times y squared. So we have 2x, that's our function in terms of x. We have y squared, that's our function in terms of y. So we can separate these. So the first thing you want to do is write the differential equation with the Leibniz notation. And then really when we talk about separating these differential equations, all we're talking about doing is putting all of the y's on one side and all of the x's on the other. And the way we do that is just through normal algebraic operations. So for instance, we have a dx on the bottom here. So to get rid of this, I'm going to multiply both sides by dx. So when I do that, the dx is on my left cancel, and I have a dx term on the right. And so at this point, and you can see this note here, multiply both sides by dx, I still have a y expression over here. So I'm going to divide both sides by y squared. So I'm going to do that, and it's going to cancel over here on the right. And we're going to end up having dy over y squared equals 2x dx. Now I want to go back up to the beginning of the statement I was talking about at the beginning here, because now I want to address this. That y function, in this case y squared, can't be 0 because we can't divide by 0. That's the reason for this qualifier here. So now we have the differential equation separated. All of the y's are on the left-hand side, all the x's are on the right-hand side. So now at this point, what we can do is we can integrate it. So in preparation for that, I'm going to write 1 over y squared as y to the minus 2, so that I can do my power rule a little more easily. And now I can go ahead, now that they're separated and in a convenient form, I'm going to go ahead and integrate both sides. And so this is, if you notice, this is very algebraic, this whole process here. Okay, this is very algebraic by multiplying both sides by dx, dividing both sides by dy. Even this is somewhat algebraic, you know, in the sense that what I'm doing to the left-hand side, I'm doing to the right-hand side. So if I'm going to integrate the left-hand side, I have to integrate the right-hand side. So I'm going to go ahead and go to the next screen, and on that next screen you'll see this expression. And I'm going to go ahead and integrate. So y to the minus 2, bump up the power to 1 bigger when we integrate. It's going to be y to the minus 1 over negative 1. And of course, seeing as we have no upper and lower bounds here, this is we call this then the antiderivative, so we have a plus c. Because that's what happens when we have no bounds, is we have that constant of integration to give us a family of functions. And we're going to do the same thing to the other side. So it's going to equal 2 times, and now we're going to take the antiderivative of x, which means we're going to bump up that power to x squared and divide by that new power 2. And on this right-hand side, we're also going to have a constant of integration. And so and I'm showing this once, and we're really not going to go back to this step ever again. But if you think about these constants of integration, you know, those are just numbers. And so if we think about algebraically changing this, let's pretend that this is like 7. And let's pretend that this one over here is like 12. So if this is 7 and I subtract 7 from both sides, I can bring this over here and get 5. Does that make sense? So really, I don't really need numeric constants on one side. I can just put the constant on a single side. It just means it's going to be a different number. So instead of 7 and 12, I could have 5 on the right. So what we do is typically when we take the antiderivative of both sides, we combine these constants and we just stick it on the x side and call it c. And we don't worry about putting a constant over here. And so now here's the solution to the differential equation. It's got a plus c on it, so it's the general solution. It represents a family of functions. But we have separated that differential equation and integrated it. And so if we want to continue, and this is kind of something that I consider above and beyond what we typically need to do, but a lot of times when we separate and integrate differential equations, we leave them in this implicit form. In other words, we don't have to solve them for y equals. But in this case, I did. I set this, so to solve this for y equals, I would take the reciprocal of this side and then divide by -1. So I have to take the reciprocal of this side, which is this, and divide by a -1. So here is the explicit form of the solution, the general solution. General being because it's still got a c here, explicit because it's y equals. But this is really not a necessary step. A lot of times we just leave it implicit. In other words, we just leave it in this form. So there's that general solution to that differential equation. In example 10 is really kind of the meat and potatoes of this process. I would consider example 10 here in its entirety like a 9-point free response question. So notice what it's asking you to do. It's asking you to find the general solution to the differential equation. And then it's asking you to find a particular solution at y of 0 equals 1. I know it's not printed here, but it's printed on your sheet. So to start out with the general solution, that general solution is the plus c solution. We're going to start out with our differential equation. And we know it's a differential equation because we see a derivative here. And we're going to rewrite it with the derivative written in Leibniz notation, the dy dx. And then we're going to do our algebraic manipulation. So if we need to separate the y's and the x's, first of all the y's are right next to each other here, so that's a good sign. We're going to take this to the other side by adding 9x to both sides. So that's what happens when we do that. And then we're going to multiply both sides by dx. And we're going to end up with this. So now all my y's are on the left, all my x's are on the right, and I'm going to go ahead and anti-differentiate both sides. So using the power rule for the left-hand side here, the y side, I'm going to have 4 times, bumping up the y power to 2 and dividing by the new power 2, equals 9 times, bump up the x power to 2 and divide by that new power 2. And then I just slap a plus c on the right-hand side, on the x side. That takes care of both my antiderivatives. So here is the solution, and we can really leave the general solution just like this. A couple of things that we do just to make it look nicer. For instance, we're going to simplify the 4 divided by 2 and put that just as a 2. And so this is really a very, very common way to leave the solution. Note it's an implicit form. We don't have a y equals or anything. It's got a y squared on the left and an x squared on the right, and that's just fine. However, if you're not a fan of fractions, sometimes we clear those. So to clear these, we're going to multiply everything by 2. And when we do that, we're going to get 4y squared equals 9x squared. And this is kind of the interesting thing to notice when I click. Notice I didn't put a 2c here. So I've got my 4y squared, I've got my 9x squared, and really, I mean, if you think about multiplying every term by 2, we should really see a 2c here. But this gets back into the idea of having a constant of integration. A constant of integration is just a number. So if I take 2 and multiply it by a number, the result is that it's just another number. So in the world of calculus, if we just put C out here and not worry about putting 2C, that's okay. It just means it's another number. If you want to put 2C out here, that's okay too, but it's not necessary. So this is a really common form for the general solution, is just to leave it like that. We don't try to solve for y equals or anything like that. Now, these terms, since they're squared, we might expect some symmetry in our graph, and we're going to look at that and talk a little bit about that as we do the slope field. But this is really a common form, and we're just going to leave the solution, the general solution, to the differential equation like that. For the next step, what we're going to do is we're going to come up with a particular solution. So we're going to want to find a strict value here for C. So that we have, instead of a family of curves, we have a specific curve. So the initial condition is y of 0 equals 1. That might look a little strange, but this is no different than function notation. This is like saying f of x equals. So we can look at this and think f of 0 equals 1. So what it's saying is that when x is 0, y is 1. So grabbing our general solution from the previous page, we're going to put in 1 for y and 0 for x, and we're going to find c. So when we substitute 1 and 0 in there, we do our math. We get 4 equals 0 plus c. We get a c is 4. So that's our constant of integration. So we're going to plug that back up here, and we're going to get an equation that says 4y squared equals 9x squared plus 4. That's our particular solution. That's our single curve that we're concerned about. And this curve has to pass through this point. Okay, it has to pass through the point x comma, 0 comma 1. Okay, and we're going to graph that particular solution on the next set of slides after we do the slope field. So going back to the initial expression for the differential equation, if we want to graph the slope field, well, when I say slope, hopefully by now you're thinking derivative. So I'm going to have to solve this for dy dx, which means bringing the 9x over to the right and then dividing by the 4y. So here is my differential equation. It's just rearranged. But this is much easier to find the values of the slopes so we can graph them. And so we're going to do that then by setting up our table. This is the only way we really can do a slope field. We set up our table and we graph them point by point. So what happens when x is 1 and y is 0? So x is 1, y is 0. So 9 times 1 is 9. 4 times 0 is 0. We get 9 over 0. 0 in the denominator is a problem. That leaves a fraction that is undefined. So at 1 comma 0, 1 comma 0 is right here. We have an undefined slope field. So remember, our dashes that we draw are an indication of the slope value we get after we do the math, the number crunching. Undefined means we have a vertical line. In fact, anytime y is 0, not just here at 1, but at any time y is 0, we're going to have a vertical line, which means we're going to have a vertical line here and here, because y is still 0, and here, and all the way across the bottom. So our slope field looks like that across the bottom or across the x-axis. So we do this point by point. I'm just going to grab another point. And notice my points I start out with is where my x is 0 and my y is 0. So I go ahead and put 0 in for x, so 9 times 0 is 0. 1 in for y, 4 times y is 4, so 0 over 4 is 0. Okay, and so again, when we have to graph the steepness of the number 0, that represents a horizontal line. And that's going to happen anytime x is 0. And so x is 0 is right. X has a value of 0 right here, right here, right here, and right here. So we're going to have horizontal lines at these locations. At this location, we already have an undefined line, so anything else we draw just wouldn't really apply. So we don't worry about drawing the horizontal line there. We're going to go on to the next point, because again, when we graph slope fields, it's point by point. We're going to put a 1 in for here and a 1 in for here, so we have 9 over 4. So 9 over 4, remember when we graph slope fields, that I really basically look for horizontal lines, vertical lines, lines that have slope of 1, lines that have slope of -1. And then anything else relative to those 4 things are either going to be flatter or steeper. So 9/4 is close to 2. So I would expect to see something steeper than 1 at this location. So here's 1, 1. Remember, a steepness of 1 would be cutting across the diagonal like this. So I'm going to expect something steeper than that diagonal. So here's something a little bit steeper. It's just an eyeball guess. Now I want to talk a little bit about that symmetry I mentioned a little while ago. Remember that the particular solution was 4y squared equals 9x squared plus 4, right? And so we have some symmetry since we have a y squared and an x squared. That means what's happening on one side of the axis is also happening on the other side of the axis. So since we have that mirror image or that line of symmetry, that if this is a 2 here, then the mirror image over here would be a -2, okay? And so we would have a -2 here. Now, you notice these 2 lines also popped up. If we think about 1, 1, and putting that in this expression, the 1's cancel, we get 9/4. Well, that also is going to happen if we go over 2 and up 2. If we put 2 and 2 here, the 2's cancel, we still have the same slope, 9/4. And same with 3, 3. And likewise on this side, we're going to have those negative slopes that have the same steepness. So that's a quick way to knock off 6 points with one calculation. So now we can go on to 1, 2. So we're going to go on to 1, 2, this one right here, which means when x equals 1 and y equals 2, we get 9 times 1, which is 9, 4 times 2, which is 8, so we get 9/8. 9/8 is really close to a value of 1. So at this location, I'm going to just draw a short line that looks like it's pretty much in line with this main diagonal. And then I'm going to use my symmetry because I know my particular solution is 4x squared or 4y squared equals 9x squared plus 4. So since I have that x squared, y squared symmetry going on, that means I have the same steepness over here but negative. In other words, this y-axis is acting as a line of symmetry. And even though I don't draw it, since I have an x squared, so is this axis. So if I would graph everything down here, it would be a mirror image of everything up here. I'm going to go on now to 1, 3. So 1, 3 is right here. That's an x value of 1 and a y value of 3. So that's going to be 9 times 1, which is 9, and 4 times 3, which is 12. So it's going to be 9/12. Now this is where it gets to be really kind of an estimate. 9/12 is less than 1. So right here I'm going to have something that's flatter than this. And I don't worry too much about if it's flat enough or not. It just needs to look flatter than this. And then I'm going to use my symmetry to get the same steepness but negative over here. And I'm going to move on to 2, 1. So over 2 up 1. That means I have an x value of 2 and a y value of 1. So I'm going to put a 2 here. 9 times 2 is 18. A 1 here. 4 times 1 is 4. So I have 18/4. Okay? And again, this is just an eyeball estimate. 18/4 is 4.5. So I think 4.5 is really steep. Steeper than this. Okay? And it's all really relative. So I'm going to go over 2 and up 1, and I'm going to draw something steeper than the orange stuff. And that's, again, I'm not going to worry too much about if it's steep enough or not. It's just got to be noticeably steeper than this orange stuff. And then I'm going to use my mirror image symmetry that I have because of my powers of 2. And I'm going to draw the same steepness and negative slope over here. And now I'm going to go on to 2, 3. So over 2, up 3, right here. So an x of 2 makes this 18. A y of 3 makes this 12. So I've got 18/12. And that's 1.5. So if we think about, I notice how I'm color coding these. Okay, the green is 1. The orange is about 2. So the blue is about 1.5. So I should be shooting for a steepness between green and orange. Okay, so over 2, up 3, a steepness between green and orange. Looks kind of like that. about 1.5. So just a little bit steeper than the one that was close to 1. And then I'm going to use my mirror image that I have because my power is a 2 and put my same steepness but negative over there. Okay, I'm going to move on to 3, 1. So over 3, up 1. So if I put 3 here, I get 27. If I put 1 here, I get 4, so 27 over 4. So 27 over 4 is close to 7. Now again, if you look at the color coding, the steepest one we've had so far was this one, 4.5. So close to 7 is a lot steeper. So all I'm looking to do with this bright green one is draw something that's steeper than the purple one. So if I go over 3, up 1, over 3, up 1, right here I'm going to draw something that looks steeper than the purple one. You know, we could debate whether or not that looks steeper, but really at this point, as long as it's not perfectly vertical along the grid lines, we'll just assume that it's close enough. And then I'm going to use my line of symmetry and put my same steepness but negative over here. Then our last point is over 3, up 2. So we put in 3 here, we get 27. Put in 2 here, we get 8. 27 over 8 is somewhere between 3 and 4. So, and that's this spot right here. And so looking through my values, something between 3 and 4 is going to be a little steeper than purple. So, excuse me, a little flatter than purple, a little steeper than orange. So kind of between those two. So a little bit like that maybe. So that's flatter than purple, steeper than orange. And then I'm going to use my mirror image to get my same steepness but negative slope there. So this is what the top half of the slope field looks like. I'm not drawing the bottom half, but we have another line of symmetry right here, another reflection line of reflection here. So all of these will be reflected down. So if you notice, we have something that kind of looks like this. Now remember, the particular solution went through point 0, 1, right? So yeah, 0, 1. So I'm going to graph 0, 1 here. And I'm going to draw my best sketch. So, and remember, these slope lines are kind of directional indicators. So this horizontal slope line is telling me that if I move off to the right, I'm going to move off to the right horizontally. But these are all telling me to start curving upward. And then as I move towards that and I move past one of those, I'm going to do my best job at being kind of sort of parallel. And then these are steeper, so I got to continue to curve upward. And then I'm going to use my symmetry to do the same thing on this side. And it should look something about like that. So if you notice that as I pass this slope field, I'm pretty parallel to it. As I pass this slope field mark, I'm pretty parallel to it. And so we have a curve that looks like that. It's not a parabola. It's a little, it doesn't have the scoopiness of a parabola. It's a little flatter. And so it looks something like this. And I want to kind of point out that if we could solve this for y, it wouldn't be that hard to. We would just divide by 4 and square root. And when we square root this, we get a positive or a negative root. And this initial condition is telling us to graph the positive solution. 0, 1 is up here, and that's up where y's are positive. In other words, this particular solution here is a positive value. So we would never graph the 1 down here unless we were asked to graph something through maybe 0, -1. Okay, so this particular solution is really telling us to take the positive root. So if we look at kind of the separable differential equations, and this is the wrong essential question, we want to algebraically separate the variables. We want to integrate then. We want to put a plus c on the end, on the x side after we integrate. And then we want to solve the initial condition problem. We want to put in an x initial and a y and solve for that c so we can get a particular solution. At this time, you can do day 3 of the homework, or if you would rather try a proficiency quiz, it would be quiz B. This is a 2-part quiz sequence for this section.